Today, the topic that we'll be discussing are redox titrations. Topics are covered. I have two books to cover these. This is covered in the online book in Chapter 9, Section D by Harvey. And this is also covered by Harris in Chapter 15. These two textbooks complement each other, and they give equally good descriptions of the redox titration. What we're going to begin with, though, is discussing what we're doing in this section is we're going to be using oxidation reduction reactions. We call these redox reactions, and we're going to use a titration method such as we learned about in acids and base section, and also with EDTA. And the importance for learning about redox reactions using a titration, well, there are two really good features of this that we learn about, and these are discussed in Harris. I do like his description. It gives us information about oxidation states of different species, and it helps us to understand about the oxidation and reduction chemistry that's occurring. This would be very important in industry if we're learning about superconductors, and it's also important for environmental applications. Harris does discuss a good application of this for environmental remediation using iron. So we're going to begin our section in redox titrations by discussing a little bit about theory. And to understand the theory behind a redox process, we need to understand about what's happening at equilibrium. So when we think about equilibrium and redox processes, we're going to begin with the Nernst equation. So the Nernst equation is really a good place to start at in this section. If you recall from the Nernst equation, we learned that the potential of a cell or any kind of chemical reaction that's undergoing a redox process is equal to the standard reduction potential that we would find using tables minus 0.05916 divided by n, and n is the number of electrons that are being exchanged in a process times the log of Q. Q is our reaction quotient, and we use Q in a means to help us understand about how a process is approaching equilibrium. And we said that the Nernst equation is really important because what it shows and discusses are two driving factors that cause an electrochemical process to occur. There is a gradient of charge, and that's reflected in the potential of our cell and the standard cell reduction potential. And there's also concentration issues that are taken care of in this half of our equation, the log Q value. Question is, what happens when Q is equal to K? We said that Q represents non-equilibrium conditions, but what happens once we reach equilibrium? So let's think about the E of a cell or a reaction. A battery, for instance. When a battery discharges, it's no longer useful, and that's because all of the chemicals that make up the battery eventually are going to equal equilibrium. So what that tells us is once we reach equilibrium, there's no more movement of electrical charge. There's no more electrons moving through that particular electrochemical cell. And the cell potential is going to equal 0. And this is what we're left with when we get to equilibrium. This is a really nice way to use standard cell reduction potentials to learn about equilibrium constants. If we equate these, it gives us information about equilibrium processes in equilibrium. But the fact that the cell goes to 0 is really important as we start to approach and learn a little bit about a redox titration. And the way we're going to approach this problem and learn about redox titrations is to discuss an experiment that we didn't get a chance to do. And I really feel sorry about that. But I want to share it with you. What's happening to help us understand about redox processes. I have a PowerPoint that's prepared, but I'm going to go through this. And to understand a little bit about redox processes, taking into account a little more of the theory that we just discussed, we're going to look at an arrangement of an experiment that we were going to conduct. And this is the iron potentiometric experiment, FE-POT. We really didn't get a chance to go through this experiment, but we're going to learn a little bit about redox titrations by addressing this particular experiment. So let's take a look at the PowerPoint that I have prepared for you. I'm going to try to draw it so we can understand what's happening in the process. So in a titration, as you recall, we have a species that's in a burette. And let's just imagine in this burette, we're going to have a solution that's our titrant, and it's composed of cerium-4 positive. And we're going to introduce it into this square environment. It could be a beaker. And it's an aqueous environment. And in that environment, we're going to have iron 2. And so we can start to see how this is sort of looking like our titration experiments, but we're going to add something to measure because we need to make a measurement to give us some information about what's happening. We're going to set up a cell. We're going to have one electrode. It's going to be right here. And we're going to call this electrode, this is going to be our reference electrode. I'll just put a 1 there. And number 1 is our reference electrode. We learned about reference electrodes in an earlier PowerPoint presentation. We normally have, for some processes, a standard hydrogen electrode, but for redox titrations, some common reference electrodes include SCE, is the saturated calomel electrode, and we also have silver chloride reference electrodes. Now, the reference electrode is designed such that it has a salt bridge already incorporated in the electrode itself. We're going to have this connected with a wire to a voltmeter or a potentiometer. So there's our potentiometer. We use the term that we like to use, potentiometer, potentiostat, and it's going to be connected to another wire down here, and we'll put that as number 2. Number 2 is going to be called our working electrode. Our working electrode is going to be inert. All we want is a surface in which we can evaluate the redox process that's occurring. A nice inert electrode that's commonly used is a platinum, PT, working electrode. And let's see where electrons are going to flow in this process using our setup here. Again, we have on the left-hand side, we would treat our reference electrode in this setup as the anode. And as you recall, the anode is where oxidation is occurring. Electrons are flowing from the left-hand side through our voltmeter and reaching our working electrode. And at our working electrode, we'll call that our cathode. That's where our reduction process is going to be occurring. So this is the idea of what we have. And let's see what we're going to measure. And let's look at the titration equation. That's really important. So we're adding cerium, +4, and we're going to react it with iron 2. And as we add one equivalent of cerium, we're going to react it with one equivalent or 1 mole of our iron 2, and we're going to generate iron 3 positive plus cerium 3 positive. So let's also recognize that this is a redox process. Cerium 4 positive is being reduced to cerium 3 positive. That's our reduction reaction. Iron 2 is being oxidized to iron 3 positive. So this is an oxidation reduction reaction. And what our measurement is going to be, it's going to be using this potentiometer. And what we're going to plot are volume additions of our cerium 4 versus a measured potential. Our potential is going to be in volts. We could also use millivolts for some cases. And what we're going to see in this particular experiment, and we're going to go through a few stages of this titration, is we're going to see a potential that rises and increases sharply right here in this region. And we would recognize that this is very similar to a titration curve that we saw for acids and bases. And this sharp rise is what we're going to use in this case for our endpoint. A drastic change in potential tells us that we've added just enough of our cerium 4 to react with all the iron 2, and we've reached the equivalence point in that particular titration. So this gives us an idea of the measurement process itself and what we're going to do. So when we think about this process and our titration equation, we need to remember equilibrium that we discussed in our last few minutes ago. It'll be in an earlier slide on my PowerPoints. Now, remember what's going to happen here. We're going to be adding the cerium, and it's going to consume some of our iron, and it's going to equilibrate. And what's going to happen is the cell is going to have no potential associated with it. Let's show what's going to happen. So I'm going to erase this part because I think that pretty much describes that. Let's erase that. It's getting kind of sloppy. And my artwork, I hate erasing it, but everybody hopefully has this image available to them. And let's write this up a little higher and just write this this titration equation. So remember from our titration equation that we showed a few minutes ago, not sure if those are the same order on that side, but it doesn't really matter. Let's write down Now notice cerium is being reduced to cerium-3 positive. Let's write down that reduction half reaction. And by convention, remember, when we write our reduction half reaction, we write it as a reduction reaction. So really, we're not changing anything here. We would look into a table and we would see this standard reduction potential that's happening for reduction, and we can think of this similar to a cathodic reaction. And we would see in a table, this has an E naught of positive 1.70 volts. So that one, no tricks. That one's pretty easy to see. It's our reduction half reaction, and that's the standard reduction potential for our half reaction that's going to be reductions occurring. Now we get kind of tricky here. Let's look at the oxidation half reaction. And we can think of this as being what we would happen at an anode if we were separating these cells completely. Now, the oxidation half reaction, we would recognize from this equation, we're oxidizing iron 2 to iron 3 by losing an electron. But let's write the standard reduction potential for that process. That's what we're going to use. And this is where it gets kind of, students get confused. The standard reduction potential is for iron 3 positive gaining an electron to form Fe2 positive. It's the reverse of what we have written in our overall equation. And we would find in our tables that this has a positive 0.767 volts. So far, everybody good with that? Even though this is an oxidation, we find the standard reduction potential from our tables. Okay, remember at our working electrode, we're measuring a process occurring. And what we would write, the E for the reaction that we're going to be measuring at our working electrode is accounting for the E for our reduction half reaction. And remember, by convention, this would be where we would have our cathode. So that's basically how we wrote this in our earlier discussion about a cell arrangement, minus the E for our oxidation half reaction. And this is what would happen if we had a cell at an anode. So this is the E of the reaction that we're measuring at our working electrode. And now let's just replace both of these reactions that make up this working electrode reaction. And remember, upon each addition of our analyte, our titrant, ceric-4 positive, when this equilibrates, this is going to go to 0. And what we get, the E for the reduction half reaction is equal to positive 1.70, which is our E naught value, minus 0.05916, divided by n. N is equal to 1, so we don't even have to write that. It just makes it sloppier. Times the log. And remember, right now, let's just write down it's going to be the log of the concentration, ceric-3, divided by the concentration, ceric-4, minus the E for the anode. The E for the anode accounts for the E naught, positive 0.767. Minus 0.05916 times the log iron 2 divided by iron 3. Remember, we write this as a reduction reaction, the way we have it written here. So what this tells us, upon each addition, since the overall reaction is going to equilibrate, either of these processes can be used to write the potential that we see in the experiment they're equal. And what that tells us, we can use either of these equations to calculate the cell potential during a redox process. I wanted to go through that because that's a little bit of the theory of what we're looking at during the course of the titration. And what we're going to show is that early in the titration, we're going to have a lot of our analyte, iron 2, and when we add amounts of serum Steric 4, we're going to be able to use the half reaction in which we're having our iron 2, iron 3. This half reaction is going to be used in the early stages of the titration. Once we get past the equivalence point, we're going to have excess amounts of Steric 4 and Steric 3 positive, and we can use this equation for the second half of the titration past the equivalence point. When we get to the equivalence point, we're going to deal with that in the discussion of developing the titration curve. So this, I hope, helps to understand why either of these equations can be used to calculate the cell potential at our working electrode. We could easily use this early, the Steric 3 positive, Steric 4 positive. Problem is, it's very tricky because this gets consumed completely and there's not going to be a lot of this, and it's really kind of hard to use that particular reaction early in our titration. Likewise, later in the titration, once we use up all of our iron 2, there's only going to be a small amount of it left. And this is going to be hard to use later in the titration. So let's go through some experimental conditions now. There's our titration equation. And we're going to look at a titration. And like we've done in our other experiments, we're going to use different points throughout the titration process. And we're going to look at some information that's given to us. And this is a problem that I have posted on today's PowerPoint, so you can refer to this. So this is our titration experiment. And this is our example. So in this example, we're going to titrate 50 milliliters of a 0.1 molar iron 2 positive with 0.1 molar of our Steric 4 positive. And what we're going to do is we're going to calculate the potential, the cell potential at the working electrode. And we're going to look at it for different additions of our steric 4 positive. So we're going to look at different conditions. 10 milliliters, and this is added steric 4. 25 milliliters. 50 milliliters. And 60 milliliters. Gave you a lot of information. Hopefully people are starting to think of what's a good first step to do. I gave you enough information is to find out when we're using these different volumes, well, what region are we in? Are we before the equivalence point? Are we at the equivalence point? Let's find out what the volume to get to the equivalence point is. Remember, the equivalence point, in this case, it's a 1-to-1 reaction. So it's when the number of moles is equal to the number of moles of iron 2 we originally have. We can figure this out. We have 50 milliliters of a 0.1 molar. That's 5 millimole. And to figure out the volume of our steric to reach the equivalence point, volume of Ce4, we put the number of millimoles divided by the molar concentration, 0.1. And we can see that this is going to be 50 milliliters. That's our volume to reach the equivalence point. Probably could have figured that out simply by inspection. Everybody good? Let's go through our titration now. So we're going to look at the first stage of our titration. And we're going to look at calculate the cell potential when we've added 10 milliliters of steric 4 positive. And we would recognize this is occurring before the equivalence point. The equation that we're going to use to solve this beginning problem, the E that we're going to use is going to be the half reaction that represented the iron 2, iron 3 cell potential. Everybody good? This is what we're going to use to solve in this region. So what I'm going to do is use a table. Real similar. This is real similar to buffer types of problems. Let's set up a table. And our table is going to be looking at the process that's occurring. And in our table that we're going to use, we're going to work with millimoles. And we're going to find out the initial amount in millimoles. The change of millimoles. And then the final number of millimoles that we have remaining. So let's add to our table. First thing we need are the initial number of millimoles of our seric 4 positive. We're adding 10 milliliters This is for our seric 4 positive. We have 10 milliliters, and we've added 0.1 molar We've added 1 millimole. I'll just put a 1 in there. We know that's in millimoles. It's kind of sloppy. We've already calculated the number of millimoles of iron 2, but just to remind you, iron 2 is 50 milliliters of the 0.1 molar. It's 5 millimole. And let's put that into our table. Well, what happens as we add 1 millimole of the seric 4? It gets consumed by 1 millimole of our iron 2. And we make 1 millimole of iron 3 and 1 millimole of serous 3 positive. What do we have when we're left? Ce4 positive is gone. We have 4 millimoles of our iron 2. We have 1 millimole of our iron 3 and 1 millimole of the cerium 3 positive. So what we're going to plug into our ratio right here is just the number of millimoles. We should put in concentrations, but the volumes, since it's a ratio, are going to cancel out. Let's put in 4. And this is 1. Let's erase our table. And if we plug these numbers into our calculator, positive 0.767 minus 0.05916 times the log of 4, the E at 10 milliliters is positive 0.731 volts. So far, everybody got that? Any questions? Send me comments. I'll be answering them online. Let's move to our next. We did this one. That one's done. Let's move to 25 milliliters. You know what? You're going to be happily surprised that this is real similar to the Henderson-Hasselbalch equation. So let's just keep that. Let's write down the potential. And let's move to our next state, 25 milliliters. And this is for Fe2 over Fe3. So what happens when we get to 25 milliliters? Well, we're halfway to the equivalence point. And if we used our table, we would see that we've converted half of the iron 2 into iron 3. This log value is going to be equal. So at 25 milliliters, we're halfway to the equivalence point. We've converted half of iron 2 into iron 3. That's half. That's half. So guess what? Log of that's 1. Log of 1 is 0. Our potential halfway is equal to the standard reduction potential for the iron 3 being converted to iron 2. And we're getting an increase in our cell potential. Again, we said that we'll draw the titration curve when we're all done. $50 milliliters. We're at the equivalence point. Okay, so what happens at the equivalence point? We've used up all of our iron 2 positive, and we've converted all the cerium 4 positive into cerium 3. And what we find out is that these two will be equal, and these two will be equal. And what we do at the equivalence point is we use a little trick. It's pretty easy at the equivalence point. At the equivalence point, the E for the cell is simply the E naught for our iron 2, iron 3, plus the E naught of the cerium, ceric 4, ceris 3 positive, divided by 2. So we can plug these in. These are simply the table values that we have at the equivalence point. This is positive 0.767 plus 1.70 divided by 2. And at the equivalence point, our potential that we measure is now up to 1.23. So far, everybody happy? Again, questions, send them to me. We'll go over this. Let's do one more, 60 milliliters. Okay, we're beyond the equivalence point now. We've added excess amount of this ceric 4 positive. We've consumed all of our iron 2. And the best way to solve this problem is because we're going to have nice concentrations. We're going to have excess of this ceric 4, and we're going to have some ceric 3. And we're going to use the E, in this case, for this cell, is the half cell reaction for the ceric 4 positive, ceris 3 positive. And here's our cell potential that we're going to use. Let's set up our table once again. Good. Let's set up our table just like we did before to help us see where we're at. And let's take into account millimoles again. We're going to take into account an initial number of millimoles of each of these species. The change that occurs and the final number of millimoles that we have. Steric 4 positive. We've added 60 milliliters of a 0.1 molar, and that tells us we're adding 6 millimole. Let's put that number in here. There's 6 millimole. Remember, we had 5 millimoles at the beginning of the day. There's still 5 millimoles in there at the very beginning. And what happens? Well, this is going to lose that 5, and it's going to take it from 5 off of here, and we're going to create 5 millimoles of Steric 3 positive and 5 millimoles of our iron 3. And the final that we have left over is 1 millimole excess and 5 millimoles that we've titrated for the Steric 3 positive. Let's put those numbers into our expression up here from our table. This is 5 millimoles. This is 1 millimole. And we can calculate our cell potential. Positive 1.66 volts. Let's think about the titration curve now. So this is the curve that we're generating. Volume of the Ce4 positive versus the measured potential and voltage. And we're starting low. We're starting down here around 0.7. And it's going up to 1.23 at the equivalence point. And then it starts to flatten out there as we get up to 1.66. And that's the appearance. We're starting at a low potential and working towards a higher potential. That's the experiment for doing a redox titration that's very similar to what we would have done in our iron potentiometric lab. Got any questions? Feel free to send me an email. Add some questions on the discussion board. I'll do videos for anything that you guys want to talk about. Look at my PowerPoints, and good luck out there. Have a nice Saturday.